Hello everyone. This is a problem from Putnam's Math 2015. It's a B3 problem, which means that it says it's supposed to have a reasonable difficulty level. And one of the reasons I'm taking up all the linear algebra problems from Putnam is because linear algebra is one of the three main components required if you really want to understand deep into the AI and machine learning. So linear algebra is important for machine learning, and by doing the tough problems in linear algebra also improves your problem solving capability required for uh, understanding the algorithms and machine learning. So let's take a look at this problem. So we have this matrix M, A, B, C, D, and its entries A, B, C, D are in arithmetic progression. Okay, and then we need to find all matrices M in S for which there is some integer k greater than 0 such that m to the power k is also in S. That means what we need to try to do is use square this m. First of all, we'll take m as elements having arithmetic progression, and then we will try to get a feel of how if you square m square, m cube, m to the power 4, m to the power k, do they look like getting towards being an arithmetic progression? And if so, how do you choose them? That is the question. Find all matrices. What are those interrelationship between A, the first term, and the common difference D, such that this M will have a higher order which will also be in AP? That is the essence of the question. So to start with, we'll write this M as elements with arithmetic progression: A plus D, A plus 2D, and A plus 3D. It's also possible to write this matrix as A minus 3D, A minus D, A plus D, and A minus 3D. That will make it look more symmetrical and make possibly the problem a little easier, but I will let you do this problem with this set of entries, but the end result is going to be same. So I will just go ahead with this one. What we are trying to do here is take a look at how we can find the higher order of this matrix. And we know that for the 2 by 2 matrix, the Cayley-Hamilton theorem reduces to m square minus trace of m multiplied by m plus determinant of m multiplied by unit matrix I equal to 0. And this is true for 2 by 2 matrices. So m square minus trace of m is just the sum of these two. So we have 2a plus 3d multiplied by m, and then determinant of m is a multiplied by a plus 3d, and then minus a plus d into a plus 2d, and this whole thing multiplied by unit matrix equal to 0. Now you could quickly, if you remember, it's good. If not, you could also derive it. For example, the Cayley-Hamilton theorem has its base which by finding its characteristic form polynomial, which is m minus lambda I, and if you find a determinant of this is equal to 0. So for 2 by 2 matrix, it looks like that A minus lambda, B and C and D minus lambda is equal to 0, and this will lead to A minus lambda into D minus lambda minus BC is equal to 0, and then lambda into lambda is lambda square minus A plus D into lambda, and then plus AD minus BC is equal to 0. Now A plus D are the diagonal element which we also, and sum of these is called the trace. So I write trace of M multiplied by lambda, and AD minus BC is the determinant of M. Now the Cayley-Hamilton theorem says that the matrix M will satisfy this equation. So M square minus trace of M multiplied by M plus determinant of M multiplied by this unit matrix I is equal to 0, and we are taking this result to write this thing for this particular matrix M, which has its element in arithmetic progression. And the key idea or key incentive for doing this is to see how we can express the higher order of M in the lower orders of M, and then investigate or try to see how does M is going to look like. Is M square forms an AP? If so, under what condition? If M square is not in AP, we will go into the even higher order, M cube, M4, and so on and so forth. The picture will clear only when we start doing this thing. So that is what you need to do in some exam. You keep trying this thing, keep writing something with certain thought process that I'm going to try here. So I can write M square minus 2a plus 3d, and we need to simplify this one. So we have a square here and then a square here, they get cancelled out, 3ad, and then we have minus 2ad and minus 2ad. So this is, and then we will have minus 2d square times of I equal to 0, and this 3ad term cancel. So what we actually, if you see, then we can express M square as 2a plus 3d into M and plus 2d square times of I. That is how we can express M square in terms of the lower order of M, and that will form the basis of our discussion from here onwards, and from here we can move forward. What is our kind of an ideal situation if we could express M square as a linear factor of M multiplied by a constant? Then since M is in arithmetic progression, M square will also be in arithmetic progression. So with that process, what if 2d square is equal to 0, which means that this common difference d is equal to 0. Under such condition, we can express M square as 2a times of M, and because M has elements in arithmetic progression, 2a plus 3d, 2a, if you multiply this one, then M square will also be in arithmetic progression. So how does this d equal to 0 mean? D equal to 0 means M will equal to look like a and A, which means that all its elements are same. So this also technically is an arithmetic progression, elements in arithmetic progression with common difference 0. And under such condition, the m square, the k is equal to, that we are asked, is equal to 2, and m square, the elements of the higher orders of m are given by 2a multiplied by a, and a. For example, if you take all elements as 1, 1, 1, 1, then 2, 2, 2, 2 is that m square value, and those elements are also in arith. And for that matter, you can take any value of m. So this is looks like one solution. Not looking very elegant, but this is a solution technically. Now, the other simplification comes from the fact that what happens if this term is equal to 0. So let's say we have 2a plus 3d equal to 0, and in such case we can express m square as 2d square into I. Now we note that if we could somehow express m square as a factor of m, as a linear factor of m, some order of m, then our problem is solved. So for that matter, if I multiply this equation by m, I get m cube is equal to 2d square multiplied by m. And now, because m has elements in AP, if I multiply this by this constant 2d square, those elements are also going to be in arithmetic progression. So with that said, under what condition it happens? The condition is 2a plus 3d equal to 0. We can express this as 2a is equal to minus 3d. I would like to parameterize it by writing a by 3 equal to d by minus 2 is equal to t, or a equal to 3t and d equal to minus 2t. And in that case, the elements of m are going to look like 3t, and then 3t minus 2t is t, and 3t minus 4t is equal to minus t, and 3t minus 6t is minus 3t. So this is how this elements of m has to be this thing, and under such conditions this m cube will have elements which are the, in that case, m cube is equal to 2d square, which can write it as 2 times of 2d whole square, or 8t square multiplied by 3t, t, minus t, and minus 3t. So one thing we can, for example, if m is, if I take t equal to 1, then m seems like 3, 1, minus 1 and minus 3, and m cube is going to look like 8, he multiplied this whole thing, so 24, 8, minus 8 and minus 24, and you can see that this also is an arithmetic progression with common difference of minus 16. So our final answer is m has to be have an element something like 1, 1, 1, 1, or m must have an element or a linear multiplication of 1, 1, 1, 1 multiplied by lambda or so, or the elements of m has to be something like lambda times of 3, 1, minus 1, minus 3. And under that second condition, k is equal to 3, the third power of m is going to be in arithmetic progression, have elements in arithmetic progression. So these are the two sets of matrices which will satisfy this condition and they too will have different values of k. Now, one thing I have not explored is that, are these two sets of solutions the only solutions, or there could be some linear combination of these, or something could also have power which will be which will also have elements which are in form the arithmetic progression. So this is something I will, maybe you can think about it, or I will think and maybe create another video of it. But thanks for taking a look at this.